All right, everyone, we're jumping into chapter 9, looking at section 9.1, significance test, the basics. So, the learning targets for this section are they, to be able to state appropriate hypotheses for a significance test about a population parameter, interpret a p-value in context, make an appropriate conclusion for a significance test, and interpret a type 1 and type 2 error in context, and give consequences of each error in the given setting. All right. So we just finished talking about confidence intervals, which is one of the two most common ways to talk about statistical inferences. What we mean by that is we're trying to infer something about a parameter. So we use a confidence interval to try and give us a range or an interval to narrow down what that parameter could be. The second method of inference is called significance testing, which allows us to weight the evidence in favor or against a particular claim. So where a confidence interval gives us that interval of where we think the parameter might be, a significance test allows us to kind of decide maybe is it bigger than or less than a given value and go from there. So a significance test or hypothesis test is a formal procedure for using observed data to decide between two competing claims called hypotheses. The claims are usually statements about the parameters. So the claim that we weigh evidence against in a significance test is called the null hypothesis, and it's abbreviated as H naught or H sub 0. The claim that we are trying to find evidence for is the alternate hypothesis, and it's abbreviated as H sub A. So let's look at this quick example. A free throw shooter claims that his long run proportion of made free throws is 0.8. But we suspect that that player is exaggerating. So he says he makes 80% of his shots. We think it's probably less. So in this case, our null hypothesis is a statement of no difference. So we'd say, okay, let's start with saying, okay, maybe the true proportion, it really is that 0.8, like he says. But we think that it's less than 0.8. So our alternative hypothesis is P is less than 0.8. The alternative hypothesis is one-sided if it states that a parameter is greater than the null value, or if it states that it's less than the null value. Or the third option is the alternate hypothesis is two-sided if it states that the parameter is different from the null value. It could be greater or less than. It doesn't really matter in context. So in that last example we did, if it was less than, we'd say, okay, he probably makes less than that 0.8. We think he's exaggerating. So our alternate would be less than 0.8. If we think he's being very modest and he's actually a lot better of a shooter, we might think that his true proportion is greater than 80. So we would look for larger than 80. And if we think it's two-sided, so we don't really care if it was greater than or less than 80. We just think that 80 is an incorrect estimate. So then we would use a two-sided test. And we showed these by less than, greater than, or not equal to symbols. Here's another problem. At the Hawaii Pineapple Company, managers are interested in the size of pineapples grown in the company's field. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in the field after the growing season. Managers wonder if the change will affect the mean weight of pineapple growth in the field this year. State appropriate hypotheses for performing a significance test. Be sure to define the parameter of interest. So our null hypothesis, or H naught, is that the mean is equal to 31, and our alternative is the mean is not equal to 31. Now it's important that we use not equal to and not greater than or less than, because we really are looking for a change. They're probably curious if it makes it bigger or less than, because if it's bigger, maybe they're getting too much water, or they're getting too big, and if they're smaller than, maybe they're getting too small. So there's a little bit of value in seeing either side. So that's why here we're looking just for any change in it and saying that it does not equal for the alternative hypothesis. And as always, we want to label, like it says here, be sure to define the parameter of interest. So mu, the true mean weight of all pineapples grown in the field this year. So we always want to label our variables so we know exactly what we are talking about. A couple tips. The hypotheses should express the belief or suspicion we have before seeing the data, which makes sense. We wouldn't make hypotheses after we saw the data because that's just going to skew our view of what the hypothesis should be. And another AP tip, hypotheses always refer to the population, not a sample. Be sure to state HO and HA in terms of a population parameter. It is never correct to write a hypothesis about a sample statistic such as p hat is equal to 80 or f bar does not equal 31. We're always talking about the parameter. So we're going to transition a little bit to what p-values are, and we're going to interpret them a little bit. So player who claimed to be 80% free throw shooter made only 32 out of 50 shots in a random sample of 50 free throws, or a p hat of 0.64. So right off the bat, this gives us a little bit of evidence that the hypothesis of PA against the hypothesis that P really is equal to 0.8 and in favor of the alternate hypothesis, which is P is less than 0.8. This is, and the question is this convincing? This is similar to when we did confidence intervals and we started with that point estimate. We got a P hat, and then we said, okay, well, yeah, that gives us some evidence, but how good is that evidence? Or what does it really mean? So that's when we had to create the margin of error, and we added and subtracted to get our interval. Same idea here. We have some evidence, right? We have a P hat less than our P, but how good is that evidence? Well, we took 400 samples of 50 shots, given or assuming that the P really is 0.8, and we see that getting only 32 out of 50 shots or 0.64, it only occurs 3 out of that 400 times. So only occurring 3 out of 400 times is a very small probability. So we know that this evidence might actually be pretty convincing. Right? And the probability, that exact probability, that 3 out of 400 is basically the p-value, the probability of getting the point estimate or the statistic and less than or greater than depending on what the alternate hypothesis is. So here, the true definition of a p-value of a test is a probability of getting the evidence of the alternate hypothesis, HA, as strong or stronger than the observed evidence when the null hypothesis is true. So it's important. We're assuming that P naught is or H naught is true, and then we're going to see how likely is it to get something as dramatic as this result, knowing that H naught is true. So here, our p-val, we had 3 that 0.64 or more dramatic out of 400 attempts and get a p-value of 0.0075. So we're going to see, is that really convincing? Well, we'll talk a little bit more about how we calculate that p-value, but we want to focus on interpreting that. So is that really convincing or not? And I would say, sorry to go forward, it probably is, right? That's a very, very small percentage. That doesn't even happen 1% of the time. So it's pretty convincing that maybe something fishy is going on. All right. Here's another problem talking about our p-values. So calcium is a vital nutrient for healthy bones and teeth. The National Institute of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers aren't getting enough calcium on average. Is this true? Researchers decide to perform a test. So H naught, or the null hypothesis, is that mu is equal to 1,300, and we're going to see if it's less than. Now, the important reason why to see if it's less than is if it's super important, we probably want to make sure that they're getting at least that. We're not too concerned if it's more than that. I don't think that having too much calcium is going to hurt us. It's not a dangerous thing. So that's why we're really only worried about if it's less than, if we're even getting that much. We're not too concerned if it's going above and beyond it because it's not going to really harm us anymore. And then after they state the hypothesis, they do state what mu is. So they say mu is the true mean daily calcium intake in the population of teenagers. All right, then they do some sampling. So they ask a random sample of 20 teens to record their food and drink consumption for one day. The researchers then compute the calcium intake for each student. Data reveals that X bar, or the sample mean, equals 1,198, and the standard deviation is 411. Researchers perform a significant, so right off the bat, again here, taking this one sample, right off the bat, we have a little bit of evidence that, hey, maybe the mean is less than, because a 1,198 is certainly less than 1,300, but the question is, how significant is it? All right, so if we continue reading, researchers perform a significance test and obtain a p-value of 0.1404. And they ask us to explain what it means for the null hypothesis to be true in this setting and interpret this p-value. So right off the bat, explain what it would mean for the null hypothesis to be true. If H naught, which is the mean is 100, is equal to 1,300 is true, then the mean daily calcium intake in the population of teenagers is 1,300 milligrams. So the idea of the H naught being true is pretty self-explanatory. It just means that, okay, we're going to assume this is true. Part B, that was probably a more interesting question, is seeing what does that p-value tell us? So we always, when we're talking about the p-value, we always assume that H naught is true. So we assume the mean daily consumption intake in teen population is 1,300. There is a 0.1404 probability of getting a sample mean of 1,198 or less by chance in a random sample of 20. And that's basically 14%. So 14% of the time, you'd get something like this just by chance. And so that's pretty high, actually. It's almost 1 in 5, between a little bit less than 1 in 5. So it's pretty high. So maybe this example isn't super convincing. We'll talk about exactly where p-values are. So we make a decision based on the strength of the evidence in favor of the alternate hypothesis and against the null hypothesis, as measured by the p-value. So that p-value is going to determine, is it significantly significant or not? If the observed result is unlikely to occur, so like in that first example, let me see if I can go back. Here, the p-value is super, super small, right? 0.0075. So if the observed is unlikely to occur by chance alone, when H naught is true, so we have a super small p-value, we will reject HO. Basically saying we're assuming HO is true, we get a very small p-value, so it's very unlikely to get something to be true based on this H naught being true. So we're going to reject that H naught. We don't really think that H naught is true because if it is true, we should get this other statistic more often. On the flip side, if the observed result is not unlikely to occur, so the one we just saw where it was 14%, when H naught is true, so if you have a large p-value, we will fail to reject H naught. And I know it sounds a little funky, but we'll start to see it come into play a little bit more. So there's two conclusions to be made. There's two things to note. Two conclusions to make. Either what's highlighted in purple or green. If the p-value is small, we reject HO and conclude that there is convincing evidence for HA. So in that basketball problem, the p-value is really small, so we reject H naught. We reject that they're an 80% free throw shooter, and we have convincing evidence that the true proportion is probably less than 0.8. The second option is if the p-value is not small, we fail to reject H naught and conclude that there is not convincing evidence for HA. So in the calcium one, our p-value is not small, so we fail to reject that the mean calcium intake is equal to 1,300, and we don't have convincing evidence that it's less than that, because that's pretty likely to occur out of chance. So it's probable that it could happen, and we don't really have that point estimate. Although it's smaller than the true proportion, it's not significantly strong enough to claim that there really is a true value less than it. So how small does p-value have to be used to reject H naught? Well, before we basically used 5% as a statistically significant event. And so this is equivalent to saying a p-value less than 0.05 or smaller. So that's what we were using in chapter 4. Sometimes it may be useful to use a 0.01 or 0.1. That would be a 1% or a 10% boundary. It just kind of depends on where you are going and how you're going to draw your conclusion. So that's the significance level, that 0.5 or 0.1 or 0.01 is our significance level, and we call it alpha. And it is the value that we use as a boundary for deciding whether an observed result is unlikely to happen by chance alone when the null hypothesis is true. So if the p-value is less than alpha, we say the result is statistically significant at the alpha level. This is very similar to confidence intervals, saying we are 95% confident that the interval from blank to blank captures the true proportion, which we probably wrote a ton of times. Here, we are statistically significant at that alpha level, whatever that alpha level is that we choose to do. And again, we should choose our alpha level before we start doing our data collection and proceed with conclusions, because that's going to change. Because what happens if you got, say your p-value was 0.06, right? Then someone might say, oh, well, I'm going to use my alpha value of 0.1 because then 0.06 is less than alpha 0.1, so I get to reject. And it's like, well, that kind of defeats the purpose, because what happens if before you're going to use an alpha value of 5%? Then it gets kind of fuzzy there of, did you actually care about the significance, or are you just trying to pick a value that will help determine what you want to determine? So we should always pick our alpha level before we do any data collection. All right. So looking at another example, a company has developed a new deluxe AAA battery that is supposed to last longer than its regular AAA batteries. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours on continuous usage on average. The company selects an SRS of 15 deluxe AAA batteries and uses them continuously until they are completely drained. The sample mean lifetime is X bar is equal to 33.93 hours. A significance test is performed using the hypotheses H naught, where the mu is equal to 30, and the alternative where mu is greater than 30. Again, we're curious if mu is greater than 30 and not less than, because we're trying to see if this new battery truly is larger than 30. So that's kind of why we decided that larger value. And they state where mu is the true mean lifetime in hours of deluxe AAA batteries. Now, if you're confused, hey, wait, well, why is mean 30 or 33.93 hours? Like, which one is it supposed to be? Remember that our hypotheses are always based on parameters, so it's always mu. Okay, right off the bat in this problem, I can see, okay, well, I'm definitely not going to use 33.93 in my hypothesis because I have an X bar. But we also know that when they're talking about the population of regular AAA batteries is how they got that 30 hours. They say the company knows that its regular AAA batteries last for 30 hours on continuous use on average. So they know that value. So that's basically saying that's the population. So my mu is going to be 30. All right. They then stated what mu is equal to. And I actually flipped this a little bit. They then say the resulting p-value is 0.0717. What conclusion would you make at the alpha level of 0.05? I would have this alpha level before you show that p-value, because again, it's kind of fuzzy, like, oh, where'd you get this p-value from, and do all these calculations. You would want to make sure that you state this alpha level earlier, so it's not just coming up to trying to be useful for you, especially because it's really close to what that p-value is. You want to make sure that you know and have decided your alpha level before you've done any of the calculations. But let's go ahead and answer this question. So what does that mean? Well, our p-value is larger than our alpha value. So because the p-value of 0.0717 is greater than alpha, which is 0.05, we fail to reject HO, which means if we fail to reject HO, we don't have convincing evidence that the true mean lifetime of the company's deluxe AAA batteries is greater than 30 hours. This is a caution to everyone. We never accept HO or conclude that HO is true. We either reject HO or we fail to reject it. Either we have statistical evidence against it or we don't have statistical evidence against it. We never really get to prove that HO is true or get to conclude that HO is true. Okay. Remember at the start of this, we're assuming HO is true and now trying to test to see, okay, did this evidence back up that claims or did it not back it up? Did it refute it? So it breaks it, we reject it, or does it fail to reject it? We don't have statistical evidence against it, but we don't know exactly where it might land. So AP in our book kind of recommends these two sentence structures for when you're trying to determine the significance test and writing your conclusion. So first, you should give a decision about the null hypothesis. Either you reject or you fail to reject based on the explicit comparison of the p-value. So if we look at the statement we wrote, because p-value is greater than alpha, so that's our comparison, we fail to reject. That's the first statement. And then the second sentence is we should provide a statement about whether or not there's convincing evidence for HA in context. So here, since we fail to reject HO, we do not have convincing evidence of the true mean lifetime of the company's deluxe AAA batteries. If we reject HO, so we're saying HO is false, then we would have significant or convincing evidence in favor of HA. Right. And that's kind of the gist of determining p-values for right now. Like I said, we'll try and figure out and calculate how do we get those p-values. But for right now, we're going to look at some types of errors we might make using these significance testing. So when we draw a conclusion from a significance test, we hope our conclusion will be correct, but sometimes it is wrong. So here's the definition of two types of errors, but I think a little chart in a second will help. We'll make it a little bit more clear. So a type 1 error occurs if a test rejects HO when HO is true, and that's basically saying that we find convincing evidence that HA is true when it really isn't. And type 2 occurs if a test fails to reject HO when HA is true, and that is the test does not find convincing evidence. So I think this chart's a lot easier. There's a couple options. Either H naught is true or HA is true. Okay, so either one of those in the real world. We don't know which one. It could be one of those two. And then we either conclude we either reject HO or we fail to reject. So right off the bat, if HO is true and we reject it, well, that's a type 1 error. We don't want to do that because it turns out that H naught is true, but we say we reject it. We don't think it's true. So that's kind of an error there because we're rejecting something that's true. A good conclusion, though, is if H naught is true or if HA is true, we're going to want to reject that HO because that would mean if we reject HO, we have significant statistical significance that HA is true, which would be the case. So that's a good conclusion. The other option is, if H naught is true, but we fail to reject HO. Again, that's good because H naught is true and we fail to reject it. We're not giving evidence for H naught, but we're failing to reject that it's not true. So that is an okay conclusion to make. Then the type 2 error occurs when, if HA is true, but we fail to reject HO, so then we're kind of saying that, HA is not true. So that's the error, the second type of error. Right, so this chart's very useful. I would probably suggest writing this down. And maybe even like when you're on the test, like at the beginning when you write your little scratch notes, this might be a good thing to write down for yourself right before a test, or as you get started for the test to kind of remind yourself what's a type 1 error and type 2 error. So let's look at an example. A potato chip producer and its main supplier agree that each shipment of potatoes must meet certain quality standards. If the producer determines that more than 8% of the potatoes shipment have blemishes, the truck will be sent away to get another load of potatoes from the supplier. Otherwise, the entire truckload will be used to make potatoes. To make the decision, a supervisor will inspect a random sample of 500 potatoes from the shipment. The producer will then perform a test at the alpha equals 0.05 significance level, with H naught, or the null hypothesis, being that that P is equal to 0.08, and H naught where P is greater than 0.08. Because the person who's accepting these potatoes wants to see, is it larger than that? Because if it is, I don't want the shipment. And they'll verify. They tell us what P is. P is equal to the true proportion of potatoes with blemishes in a given truckload. And they ask us to describe a type 1 and type 2 error here. So type 1 error is when the producer finds convincing evidence that more than 8% of the potatoes in the shipment have blemishes, when in fact it is 0.8. So we reject H naught when H naught really is true. And the reason why that's bad is that the potato chip producer sends away a truckload of good potatoes. Basically, they're gonna reject this notion or reject this hypothesis, even though it's true. And some consequences of it would be, well, you're wasting time, and you're wasting money because now you've just sent away a perfectly good batch that you now have to wait for another batch to come in. So you don't really want to make a type 1 error. You're just going to waste time and money. And those are two things businesses do not want to waste. A type 2 error, on the other hand, is the producer does not find convincing evidence that more than 8% of potatoes in the shipment have blemishes, when in fact it is true. So this would mean that the shipment of potatoes has, let's say, 10% blemishes, but we don't notice it and we accept the batch anyways. So this could be bad because we accept a bad set of potatoes, and with that we might make some worse potato chips and upset customers and maybe lead to decreased sales. So the idea of like type 1, type 2 error, you can kind of see that they might benefit or hurt one side of the party. So in this case, a type 2 error, it really hurts the potato chip company because now they're putting out a bad product. But it kind of benefits the supplier because they just got rid of a bunch of bad potatoes without any problem with it. They sold them off as if they were brand new, and they were all a little bumped and bruised. So in this, if you're the potato company, the potato chip company making the potato chips, you want to stay away from type 2 errors as much as possible. But if you're the farmer of the potatoes or the seller of the potatoes, you kind of want to stay away from type 1 errors because they're saying that your potatoes are bad when in fact they really are good. And so you've wasted all that time making good potatoes for no one to accept. So there's some good and bads to each type of error depending on which side of the aisle you fall. So we mentioned how the most significant levels for alpha is 0.05, 0.01, and 0.1. And which one of these is best for a significance test? Well, that depends on the type 1 and type 2 error is more serious. And well, why does that mean? Well, the probability of making a type 1 error in significance testing is equal to alpha, which makes sense, right? Because if my alpha or my allowance value is, let's say, 0.05 or 5%, well, it's basically like the confidence interval, my alpha level. I'm at 95% confidence interval, so I'm allowing a 5% leeway. That 5%, I'm basically expecting to make a mistake 5% of the time. So since with our significance testing, we either reject H naught or we fail to reject H naught, we're basically saying 5% of the time I'm going to reject H naught when I shouldn't. Okay, so so the alpha level is kind of determines the probability of a type 1 error. So we can decrease the probability of making a type 1 error in a significance test by using a smaller significance level. So depending on where you are in that potato problem might depend what significance level you want to be at, because if you were the producer, you really want a low type 1 error because that's hurting you. You have to go throw away potatoes that were claimed to be bad when in reality they were really good, and so you're wasting a lot of money they used to produce all those potatoes. So if you're the person making this test, you want to decrease that type 1 error as much as possible. But the trade-off, if you decrease type 1, you're going to increase type 2. So as one increases, the other decreases, and vice versa. So me being the potato chip company, I don't want you to decrease type 1 that much because now you're just increasing the probability of type 2 happening, the probability of selling me bad potatoes and claiming that. And that is basically it for today for 9.1. So you should be able to state the appropriate hypotheses for a significance test, interpret a p-value in context, and make a conclusion about it. So if I reject or fail to reject, and what does that mean? And then come up and interpret type 1 and type 2 error and give a consequence of each, depending on the setting.